really brief administrative thing. So I've brought the midterms back. They're here in the front for those of you who either show up late or are watching this after the fact. If you're watching this after the fact, obviously you won't be able to grab it here, but just come by my office and you can grab the midterm from there. In case you're wondering sort of how you did relative to everyone else, the mean was 35 and the standard deviation was about 7. So obviously there was quite a few people that went beyond the sort of nominal maximum score, which was 40. There was about 8 or 9 bonus points that you could have gotten in max. And there was a couple people that basically got all of those as well. So overall, it looks like most people did pretty well. The mean was indeed quite high, so I think that was pretty good. If you had a score below, maybe about a deviation and a half below the mean, please do come by and chat with me. I want to make sure that all the concepts that were there you're able to sort of catch up on and are more clear now that you've sort of had a chance to go through the exam and look at the solutions and all that, just to make sure that you'll sort of stay on top of the material moving forward. But other than that, as I said, I think overall it went fairly well. So, any questions on the sort of midterm itself or material so far? Okay, so just as one other sort of quick reminder, homework number 4 is out. You actually know most of what you need to know to even sort of start doing it now. As I'd mentioned before, it's actually sort of a little bit of a miniature design project. And I also strongly recommend that you come to sort of Pierluigi's office hour / discussion tomorrow, because it'll give you a whole bunch of hints on sort of how to start on that, a few sort of details about biasing and things of that nature. Okay? And by the way, by the end of today, we'll really know sort of pretty much everything you need to know to be able to do that homework in its entirety. So with that, unless there's any other questions, let's go ahead and dive back into the material. So last time we were really spending a lot of time talking about settling. And in particular, what this really meant was understanding how all these frequency domain effects, like poles, non-dominant poles, pole zero doublets, feed-forward zeros, and so on and so forth, impact us in terms of the time domain settling behavior of our amplifiers. So what we basically ended up was talking about doublets, and we sort of mentioned this a little bit briefly last time, but I want to go back through the details now to make sure that everything is really perfectly clear there. So as we had been doing before, rather than sort of doing a complete, let's say, model of some specific amplifier, in general, to sort of give us an idea of what these pole zero doublets are going to do, I'm going to just modify the sort of GM that I'm assuming is inside of my closed loop OTA to, instead of just being some transconductance, to actually have some additional dynamics, and in particular to have this pole zero doublet associated with it. Now, as we discussed a little bit last time, the way I want to define these pole zero doublets was with a few extra parameters, because as we'll see, if I use these parameters, it'll make it much more clear what the real final effect of the pole zero doublets actually are. Okay? So first, I'm going to define the extra pole due to this GM as being some factor beta times the 3 dB bandwidth of my open loop transfer function. Okay? Similarly, I'm going to define my 0 to be at essentially the same quote-unquote point as that pole is, but just divided by some alpha factor. Okay? Where that alpha factor, again, I'm just going to define as being something like 1 plus epsilon, where epsilon is some small number. Where again, the whole idea here is to say that if epsilon is small, the pole and the 0 are very close to each other in frequency, which is usually what we mean when we say a doublet. Okay? So if I just take all these definitions and I basically plug them into my sort of standard closed loop, essentially capacitive feedback OTA, then what you can end up with, at least approximately speaking, is something that looks like this. Okay? So I'm still roughly speaking going to have the same 3 dB bandwidth as I had before, but it's going to be multiplied by the 0, which was in the OTA. Okay, so by the way, notice the 0 does not actually move once we place the OTA into the feedback. And mathematically, you can see that just by, if I multiply this GM here, if I notice that there's a 1 plus S over omega Z, when I multiply the numerator and the denominator by that same thing, you'll end up with 1 plus S over omega Z in the numerator. Right? In other words, you end up with that 0 unmodified. Okay? Divided by, there's still going to be this other pole due to that to the pole in the OTA. But notice I've defined this now as omega pp. It turns out this second pole, and again, mathematically you can see this pretty easily, the second pole won't be exactly at the same place as this original pole in the OTA was. But if you've done things quote-unquote properly, it will be pretty close. Okay? So that's why I've said here, I've indicated here, this pole is roughly speaking at the omega p of that OTA itself. The 0 is still exactly where it was before. And the 3 dB bandwidth to 0 order also is not really changed from what we would have expected if we had a normal amplifier without this pole 0 doublet in it. Okay? In other words, it's still just at FGM over CL effective. Okay? So now, with all of that in mind, as we briefly talked about at the end of class last time, basically if we look at the step response of this, then we would see that essentially because we have those two poles in our system, indeed we'll end up with two sort of independent exponential settling terms, right? Yes? Okay. So the question was, why should the second pole not necessarily really move? In general, if I just came up with completely arbitrary numbers, it's not that it wouldn't move at all. It could indeed actually move. It's more just that for typical sort of designs, to the extent that that pole is reasonably far away from the dynamics we care about, and as long as it doesn't cause anything to be sort of unstable, then it won't move too much. So that's the sort of the intuition there. And again, by the way, you can kind of go through it mathematically. You'll sort of see exactly what it is I'm referring to. I'm really just making a little bit of an approximation there to split those two poles up. Okay, so the whole name of the game is that, again, I'm going to have the step response that in the time domain is going to have two independent exponentials to it. Okay? And of course, one of those exponentials is just set by my 3 dB bandwidth, just as it was before. And the second is, of course, going to be set by that secondary pole associated with the OTA itself. And so all that's really then interesting is to ask ourselves, how big is essentially the magnitude in front of each of those exponential terms? Okay? So this A term, which is associated with the main 3 dB bandwidth, that one, to the extent that our pole and 0 really are very close to each other, this should be very close to 1. Okay? It won't exactly be 1, but it should be something very close to 1. Because as you can see, this B term is proportional to that epsilon, which, as we said before, should be a very small number, right? If indeed this is a very small number, then A should indeed be close to 1. Now really, the actually much more important thing to sort of pay attention to is how big this B term really is. Okay? So first of all, as we'd said before, it's proportional to epsilon, meaning the closer you get that pole and 0 to each other, the less sort of effect this secondary exponential settling is going to have, right? But second, and perhaps even more importantly, is that notice the whole term is sort of, in some senses, proportional to beta over 1 minus beta squared, right? In other words, the larger you make that beta, the less effect this whole thing is going to have, right? In other words, you're going to decrease that B if you push that pole 0 doublet out to a frequency much higher than you cared about in terms of that 3 dB bandwidth. Okay? So as we saw in the sort of time domain, when we put this all together, again, it really just says something very straightforward, which is if I originally would have had this green curve with a simple single pole settling, now when I add this pole 0 doublet in, instead of really settling to the final value I really actually wanted, I'm going to have this additional slow settling term that will not actually, that'll take longer to finally get to the real final value that I really wanted. Okay? Now notice I actually exacerbated things pretty badly here, just to make the effect really clear, right? Notice I had a pretty big alpha, or really a fairly large epsilon, right? I shifted those things even by about 0.5 or whatever it was. And I put that beta, meaning I put that second order pole close inside of the 3 dB bandwidth I actually cared about. But nonetheless, the point is still the same, that if you end up with a response like this, then you're going to have to wait for that second order pole. Okay? So at the end of the day, what this really says is actually very similar to what we had started out with from the get-go when we talked about these sort of gain-boosted cascode type of topologies, right? Because really you can think about this as sort of two different limiting cases. The first case, which is exactly what we had said we wanted to do in the gain-boosted cascode context, was if we really just put that pole 0 doublet out at a frequency that's well beyond anything we care about, then for all intents and purposes, it's not going to have any impact on us, because that piece of things will settle faster than the main amplifier actually does, right? In which case, it won't really have any impact on our overall behavior. So this is indeed the sort of nominal solution we're almost always going to be shooting for. In other words, we're going to just try and make that pole 0 doublet sit out at frequencies that are beyond where we really care about. Now, having said that, there could indeed be a case where, for better or for worse, that pole 0 doublet is sitting inside of the bandwidth you care about, right? And unfortunately, in those scenarios, that settling will indeed sort of show up at our output. Okay? So the only point there is that unless you have a way of really controlling what that epsilon is, meaning how close the pole and 0 really are to each other, there's going to be some amount of settling error that's going to be dominated by the dynamics of that second pole, right? And if that error is larger than the error you're targeting, sorry, now this is going to dominate your response, okay? So the real trick is that oftentimes it's actually tricky to control exactly where that epsilon is, because it's basically set by other parameters you don't really have a ton of control over. And so because of that, our sort of default solution is always going to be, well, let's just take that pole 0 doublet, push it outside the dynamics we care about, and then we don't really have to worry about it. Okay? Does this make sense to everybody? Or? Okay, great. So just one sort of final note on pole 0 doublets that is kind of a fun one before we really move on to talk about the final sort of settling effect, which is that it turns out sometimes you can actually exploit pole 0 doublets to do some interesting, nice things for you. Okay? And the perhaps classical, best-known example of this actually shows up in an instrument that pretty much all of you guys should have used at some point in your lives, which was an oscilloscope. Okay? So if you sort of looked at a lot of these oscilloscopes, especially the sort of real-time ones, you know, if you look at that button on there, there's usually two options, right? One is to make the input impedance 50 ohms, and the other one is to make it a mega ohm, right? So let's just think a little bit more carefully about what the implication is of having an Rn of 1 mega ohm. Okay? And in particular, if I had an input impedance of 1 mega ohm, and I also wanted to claim that I had a bandwidth of, let's say, 1 gigahertz, how much capacitance would you be allowed to have on that little, even on just a little like, you know, connector thing that's on that oscilloscope, to actually maintain a bandwidth of 1 gigahertz with at least a DC input impedance of 1 mega ohm? How much cap are you allowed to have? And don't worry about factors of 2 pi for now. Is it a picofarad? There you go. It's actually a femtofarad. And if you include that factor of 2 pi, it's actually about 0.15 femtofarads. Okay, so does anybody think that, you know, that macroscopically sized connector thing has a capacitance of 0.15 femtofarads? Hell no, right? No way in hell. It's just not going to happen. Okay? So how in the world do you get a DC input impedance of 1 mega ohm and still actually get a bandwidth of 1 gigahertz? Which, by the way, they do actually do. All right? So turns out what they do is they exploit a pole 0 doublet somewhere. So to specifically see how that would happen, let's sort of draw an equivalent circuit for this oscilloscope input head. Okay, so what they really actually do is something like the following. Let's say I was to split that 1 mega ohm into 100 kilo ohms and 900 kilo ohms. Okay? And then indeed, there is going to be some capacitance inside of either that scope probe or just driving the sort of electronics inside of the ADC, which is going to be, let's just call it some number. Yeah, well, let's just call it C input. Okay? So, can anybody guess what's the trick that they play to actually avoid this filtering problem? What do they do? Sweep C input. Well, unfortunately, if I could make C input to 0, then yes, indeed, I could get whatever bandwidth I wanted. But there's going to be some physical cap that I just can't get rid of there. Okay? So I'm going to have to actually add something to the circuit. Oh, okay. You're really close. So, unfortunately, this wouldn't really help, right? Because that would just put sort of a lower impedance on my input. But you're really close. It is actually adding a capacitor. We just have to add it in the right place. I'll give you guys a hint. You remember how that feed forward stuff, like you make the input move and the output would immediately move too? Yeah, exactly. Okay, so what you actually do is this. You take a cap between V in, and you connect it to the output. Okay? And in fact, I'm going to make this cap tunable now. All right? So here's the trick, or here's rather the sort of conceptual idea. So let's do a plot of V out versus time for, and let me write that more clearly. So again, V out versus time. Let's do a plot of that under the assumption that the input was a step. Okay? And in particular, I'm going to claim that there's some optimal capacitance that we can use here, that if we pick it just right, will give us sort of a quote-unquote perfect bandwidth. Okay? So, and maybe I'll sort of ask you guys. So let's say that I made that capacitance larger than what the optimal is. Okay, so I really make that coupling capacitance there very big, okay, relative to sort of what the quote-unquote optimal will be. And we'll see if we can figure out what the optimal is in 1 second. Okay? What do you think the time domain response would look like? And by the way, let me give you one hint. If there were no capacitors there, what would be the ratio between V in and V out? What would be the gain of the circuit? Yeah, it'd be attenuation of 10, right? So if I put in a step of 1 volt, ideally speaking, my output should have stepped from 0 to 100 millivolts, right? All right, so now if we add this capacitor in, let's say I make that capacitor, for all intents and purposes, infinitely big compared to the capacitance underneath it. What would that capacitive divide ratio be? In other words, if I was going just through the capacitors, yeah, it'd be 1, right? Because if that cap is infinitely big, and just to be clear, right, if this cap was infinitely big, then there'd be no attenuation, at least not right away, right? Okay, so now you guys tell me, in the time domain, if I make this capacitor larger than its optimal value, what should the time domain response look like? Not quite, actually. I think Lucas did the right hand motion, so maybe just describe it. Yeah, exactly. So what'll happen is it'll jump up, it'll overshoot beyond where it was supposed to be, and then it'll start settling with whatever the time constant was to the final value, right? Okay, so now let's do another thought experiment. Yeah, so the question was, is the final value determined by the 2 resistor ratios? That's exactly what it's determined by. Right, so as we said before, at the end of the day, the final value is going to be 1/10 of the input, right? Just because of that resistive divide ratio. Okay, so let's do another example, and again, a slightly different color. Let's go with black. So let's say that you make it smaller than the optimal value. Now what will the time domain response look like? I see a few hand motions, but let's see if we can get someone to describe it. Okay, yeah, so I think you basically described it. So what will happen is initially I will jump up, right? But I won't quite get to where I was supposed to be. And then I'll have to, again, exponentially settle to whatever the final value is supposed to be. Okay? So now, as you can imagine, if I get things just right, and I'll do that, I guess, in red, right? If I do things just right, then what will happen is, and this will be, of course, k equals 1, right? It'll jump to exactly the final value and just stay there, right? So by the way, in the context of a pole zero doublet, if I set it to exactly the optimal value, where did I place the 0 relative to the pole? Yeah, they're exactly on top of each other, right? They're basically canceling each other out. Okay? So, in an oscilloscope, this is kind of okay in the sense that, you know, they can take their whole setup, they can turn some mechanical knobs or whatever it is to tweak that coupling capacitance to get things just right. And by the way, when they do calibration, that's sometimes exactly one of the things that they do. Okay? But obviously, and I'll get your question in 1 second, obviously, in a circuit context, unless you have a good way of really modifying that cap, measuring exactly what's going on, you may not be able to necessarily exploit exactly this effect. But nonetheless, this is a good thing to know about. So there's a couple questions. Maybe I'll just take Andrew's first, and then...
So then, this is what you do when you hook up, like on front, there's usually 2 prongs with that output square wave when you hook a probe up to that and turn the knob on the probe. That's what you're calibrating, right?
Typically, yes. So the question was, you know, if there's the thing where you stick in that probe and there's something that you calibrate when you turn the knob, this is typically exactly what you're calibrating. Okay? By the way, this is also exactly why a lot of those probes have a 10-to-1 attenuation. Because otherwise, if you didn't have that attenuation, it's nearly impossible to get any reasonable bandwidth out of it. Rachel?
I was just going
Oh, well, so if I'm in the lab or whatever, I can just shove in a step and then turn a knob until, things look correct, right? No, actually, they typically do it in the factory. They're just relying on the fact that things won't drift all that much until, you basically, or rather to say it another way, they tell you, look, you should bring this in for calibration every year or something like that. They've characterized their components well enough to know that every year or so is about the time constant of this thing drifting away from where it's supposed to be.
So if you happen to get, a new cheap set of probes that you bought in China or something, the interior oscilloscope and the capacitors are different, that's, you connect that with the thing to adjust the capacitance?
Basically, yes. So the question was, if you just bought some new set of probes that was uncalibrated, then indeed there might be some calibration you'd have to do just to make sure it's actually behaving the way you expected it to. Good. Other questions on this? Or? So again, the take-home message here is not that I'm saying you should necessarily intentionally do this kind of stuff left and right, but it is to say that if you really know what you're doing, and if you're careful, you can actually sometimes exploit pole zero doublets to do some interesting things that otherwise you thought would not have been possible. Okay? Okay, so the last thing I want to spend a little bit of time talking about, again in this context of settling, is the so-called slewing response of amplifiers. So I'm assuming that most of you guys have seen something like this before, but just to maybe sort of review and give you a little bit of an idea of how we're going to handle it here, specifically in the time domain, we have to remind ourselves that for almost any real amplifier we're working with, there's only going to be some finite range of input signals over which it's still going to behave as a quote-unquote linear amplifier. Meaning that if you go beyond some, let's say, magic input voltage, and we'll decide what that magic input voltage is in 1 second, then instead of the current versus voltage being linear, it'll start to become nonlinear. Okay? And in particular, the sort of most common sort of curve that you might see looks something like the following. Come on. There we go. So if we drew a plot of essentially the differential output current versus the differential input voltage, typically you'll get a plot that does, I don't know, something sort of like this. Okay? So now, you guys are all, grad students or advanced undergrads or whatever it is, and I'm sure I could give you some functional form for this curve, and you can start writing out a bunch of nonlinear differential equations and tell me in time what the response to some signal with this nonlinear transfer function is. But obviously that's a huge pain in the ass, right? I don't think anyone would particularly enjoy that exercise. Okay? So from an engineering standpoint, what we're typically going to do to model this curve is something like the following. We're going to say, well, you know what? That's too complicated, but I think I can model this pretty closely by just doing the following. I'm just going to say, look, this is basically either a straight line or completely saturated. Okay? And I'm going to do that again on both sides. I'm just going to say, look, it's either a straight line or just completely saturated. Right? And of course, the good thing about doing this is now way easier to model. Right? Because I either have a perfectly linear system or something that, as you'll notice, I just have a perfectly constant current coming out of. Okay? So now, by the way, just really as a reminder, this response typically at the end of the day is coming from some kind of differential pair in your circuit. Right? And if we keep that in mind, we can actually say a lot about what this curve should really look like. All right? So first of all, given that everything is really coming from this differential pair circuit, what do you think that maximum differential current should actually be? What is the value of it in terms of sort of the components I've labeled there? Yeah, it should just be ISS, right? So indeed, that maximum value is just ISS, and of course over here, minus ISS. Okay? Now here's the slightly more interesting question. What's the voltage at which it should be becoming exactly just ISS? When should that happen? It depends on the overdrive. So when you say overdrive, what do you mean? And I'll just give you a little reminder. We tend not to use overdrive here, but we use a slightly different parameter. Depends on the V star. Okay, so how is it related to the V star? Okay. So you said that it's root 2 V star. Turns out there's some more detailed derivations you can do that may get you to something like this. But remember, I know absolutely nothing about the real IV characteristics of my device. All I know is that there's a V star and that at some particular bias point, that V star, by definition, was related to GM and ID. Okay? So let's actually remind ourselves of that. How was the V star defined in the first place? Okay, so you said the sort of final result, but I'll just write it the way we typically remember it. GM is, of course, 2 times whatever the drain current is, divided by V star. Okay? Now, in this particular context where I have a differential amplifier with a certain ISS, what is the GM of that, the differential GM of that amplifier as a function of ISS and the V star of each individual device? I asked what sounded like a very complicated question. It turns out there's just a very small minor integer factor difference between the answer to that one and what we have written over here already. Yeah, exactly. So the differential GM is essentially just ISS over V star. Okay? So now, if that's the case, and again, this slope right here, that's exactly just our differential GM. Okay? So if that's the case, and this is kind of by definition how we've sort of set up our V star, what does this point where it hits exactly ISS have to be? 1 over V star or? V star, there we go, right? So notice this implies that if you want a differential current of ISS, that happens at exactly a V star of input voltage. Okay? So indeed, with this simple model, you're going to clip at exactly V star on the positive side and exactly negative V star at the negative side. Okay? Now again, keep in mind, this is not to say that real amplifiers behave exactly this way. If you actually look at real amplifiers, typically it really saturates out at about square root of 2 times V star or something like this, but not too critical. This is going to be a very reasonable model for us to be using. Okay? Does this make sense to everybody? Or? Okay, so now what's really nice about this is that it's going to allow us to, again, do a very simple analysis to basically include the effect of this slewing. Okay? So in particular, if we know that we're going to enter this slewing behavior, then what's going to happen is that during the time we're slewing, we're just going to get this constant current flowing from the output. And as I'll remind you guys in a second, constant current flowing from the output, of course, means a constant slope on the output. Okay? Then once we get back into the linear regime, then we'll just have a sort of exponential settling exactly like we're used to. Okay? So that means that at the end of the day, if we're interested in our overall settling time, we can just say that it's some slewing time plus that linear settling time. Okay? So to really make sure that that's clear, let's just sort of walk through a fairly simple example. And this is, again, just exactly looking at our sort of capacitive feedback amplifier. Okay? And it's really more than anything else just kind of a reminder of some things that I think you have probably seen in the past, but we'll just rehash it here to be sure it's absolutely clear. Okay? So let's again assume that we take our capacitive feedback amplifier. I've drawn here, of course, the small signal model for it. And we apply a step at the input. Okay? So right when we apply that step, and let me just maybe draw the amplifier itself just so that everyone sort of has a correspondence with a real circuit diagram. All right, so we, of course, have something that looks like this. So that's our CI, that's our CS, that's our CF, and that's our CL. Okay? So right when we do that input step, what's going to happen at the real input of the OTA? And let's just call that Vx for the sake of clarity. So what's going to happen at Vx right at the sort of instant of that step? Yeah, it's also going to jump up, right? Okay, so for now, let's assume that it jumped up enough that the OTA actually slews. In other words, it jumped up to be larger than the V star of our OTA. Okay? So if that was the case, and then I then did a plot of the output voltage versus time. And let's just assume, for the heck of it, it started somewhere over here. Okay? What would that output voltage do? And let's say that, this is right when the step hits. What would the output voltage do? Actually, you know what? Let me do it even at Vx. Okay, so let's do it a Vx so that this is right where that initial step happens. Okay? So, once the amplifier starts slewing, what's going to happen at Vx? What's the sort of shape of the waveform going to be? I heard somebody say it. Just speak up. Yeah, it's just going to be a straight ramp, right? Because I have a constant current flowing from the output of ISS, as I've indicated here, right? Some fraction of that current is, of course, going to flow through CF and be discharging Vx, right? Okay, so indeed, we're just going to have some constant ramp there. And again, just maybe as a reminder, what's going to be the slope of that ramp? Or at least in general, what's the slope of a ramp with a constant current and a cap? Is it a GM, or I heard somebody else say it? Yeah, there's going to be I over C, right? Because remember, I have a constant current and a constant capacitance. Okay? And of course, there's a minus sign there, but don't worry about that. Okay? So indeed, if I have this step that jumps over and that goes to the input of the amplifier and causes it to become sort of clipped, I'll then just start linearly slewing current of the output, and I'll keep doing that until what happens? At which sort of point will I start entering a more reasonable regime, quote unquote? Yeah, exactly. So once this thing finally gets to the V star, then the whole thing enters a more linear regime, and it goes back to our sort of more standard linear settling type of response. Okay? So let's actually look at this more carefully, but with sort of the complete amplifier. Okay? So this is really showing you kind of exactly what I showed before, but now I'm showing you both Vx and the output voltage at the same time. Okay? Because it turns out some things are easier to sort of calculate than others. Okay? So, if I look at this Vx here, right? Then again, as we said initially, when we go over V star, we're just kind of that linear ramp on the way down, right? So if we have a linear ramp at Vx, same thing is going to happen at V out, right? It's also going to be ramping with a linear slope on the way down. Now, just to be totally clear, what is going to be the slope, or what precisely is going to be the slope over in this region at V out? Now, maybe give you a little bit of a reminder here. This is sort of the equivalent circuit. So what is that slope going to be? Yeah, okay, so which I, by the way, did you mean? There we go. So that's just going to be proportional to, that slope there is essentially going to be minus ISS over what we like to call CL effective, right? It's just the total load cap at that output there. Okay? And that's exactly what that slope is going to be. All right, so now, if I go back to looking at Vx, what's the final value of Vx supposed to be eventually, once everything is settled out? Where should Vx go to? Yeah, it should go to 0, right? Eventually it should land somewhere over there, right? Okay, so as we said before, once we sort of get below V star on Vx, the whole thing should start looking like a linear amplifier, right? If it's a linear amplifier, it has some exponential settling, okay? So that would mean the whole thing would look something, let's say, like this, okay? And of course, if we did that on Vx, same thing should indeed happen on V out, just scaled by some factor, right? And okay, so by the way, just to be totally clear, what should that final value be on the output? Yeah, exactly. It's just minus CS over CF times V in. Okay? So now, one other question just to make sure things are clear. I attempted to be somewhat careful in my drawing here, but I don't know how successful I was. Let me ask you guys sort of the question to see if you can tease out what the sort of potential issue with my drawing is here. So, in which region of this waveform should you have the absolute highest slope? And I should be careful after the step has occurred, of course. So which region of the waveform should have the highest possible slope? Yeah, it's during the slewing, right? Why is it that it's during the slewing? Yeah, exactly. During the slewing, you're shoving the maximum current you can possibly shove into the output, which means you have the highest possible slope, right? So that also means that by definition, once you enter the linear region, your slope has to decrease, right? So that's why I said, I maybe was kind of okay with my drawing here, but if I was really, really careful, I would have had to make sure that the slope in that linear region was always lower in magnitude than the slope of the slewing response. Okay? And again, that's simply because slewing exactly means you've got the maximum current you can possibly get. Okay? Yes?
I just want to know, so the slope of the VX step is that also ISS, or just the sort of expected?
The slope of the Vx step, you mean right here, or you mean after it's slewing? No, so we have to be a little bit careful here. This slope is not exactly ISS over CL effective. You have to sort of figure out what the effective current flowing in that branch of the circuit is. But actually, to zero order, it's going to be pretty close. Yeah. There's just a scale factor, again, in terms of the gains between the two, right? OK, other questions on this? Or? OK, great. So if this is clear, it turns out that actually, once you have this picture in your head, analyzing the settling response even with slewing is actually pretty easy. Okay? Because all you have to do is basically figure out a few sort of simple quantities. Okay? So the first is, because it's really the input of the amplifier that controls whether or not it slews, unlike what we usually do, we sort of first have to figure out how big is the step at the input of that amplifier. Okay? Because it's only once that step sort of goes below V star would things get back into that linear region. Okay? So this first line that I've done here, all I'm really doing is figuring out how big is the step at Vx. Okay? In other words, if I put a step of Vi at the input, how big of a step am I going to get at the input of the amplifier? And fortunately, that's pretty easy to calculate, right? If we just go back to sort of this picture here, if I put in a step right there, I can very quickly calculate the magnitude of the step right there, just through essentially a capacitive divider, right? Where that capacitive divider is just set by essentially Cs relative to Ci plus the quote-unquote parallel combination of Cf and Cl, right? So if you sort of track the equations I've written there, that's exactly what I've calculated this thing to be. Okay? So now, once I know how big that step is, I then also know how much voltage do I need to move by at Vx in order to actually get myself back to V star, right? So in other words, there's just going to be a certain amount of swing that I have to do right in this region here in order to get back to V star and get back to the linear settling response, right? So that delta V, of course, is just whatever that initial step is minus V star. And as a reminder, that says that the delta V that you have at the output, if I know what Vx is doing, the output is going to do the same thing, just scaled by 1 over f, right? So that's why I can say that if I know this delta V at the input, then the delta V at the output is just that same delta V at the output, at the input divided by f. Okay? Okay, so once we know all that, then actually I claim we're basically done. Okay? Because if I know how much I have to slew at the output, and I also already know my slew rate, or my slope at the output, I can immediately calculate how long does it take me to actually get to that point, or to actually do that swing. Right? And just as a reminder, as should be expected, with anything that you have a current, a capacitance, and you're interested in time, it's always CV over I that matters. Right? So just to be sort of absolutely clear as how to get to the expression that's drawn here, this is really just saying that all we actually needed was, we of course have a CL effective. Right? The voltage swing we're doing is just delta V out, which is delta Vs over F. And our current is ISS. Okay? Right? That's exactly equivalent to what I wrote right here. I just pushed things around a little bit, numerator and denominator. Okay? All right. So we know what that settling time for the slewing is going to be. So if we have that, then the only thing that's left is to figure out how much longer will the rest of the linear settling take. Right? And for that, actually, it's again pretty easy, because we can just say, well, okay, if I have this linear thing that I know always starts right from that V star, I just have to figure out how much additional swing or how much sort of settling do I have to do to take this initial signal that started at V star and settle it out to some finite error relative to my final swing. Yes?
Sorry, when you say linear, you mean linear in
I mean linear in terms of the, like in the sense of LTI circuit, not linear in the sense of the waveform, right? Because remember, once the, and this is somewhat confusing, I agree, once the amplifier enters a linear regime of operation, that means the waveform at the output will be exponential, right? That's the thing to keep in mind, okay? So indeed, right at this sort of boundary, I can essentially say there's an initial condition of V star at the input of that amplifier. And so all I need to know is essentially how many time constants does it take for this initial condition to decay down to the error level that I want it to be at. Okay? And again, that's pretty easy to do because I can just say that that's really just set by, okay, at the output, I have this V star over F of swing that I'm going to have to do, right? And I want to compare how big the sort of error of that is relative to what my final thing is supposed to be, which is just the ideal closed loop gain times the input step. Or again, that ideal closed loop gain was just CS over CF. Okay? So this whole expression here looks kind of complicated, but really it's not. All it's saying is that I want to know how many orders of magnitude there are, or really what's the ratio between essentially my error spec times the final voltage that I want to be sitting at, relative to the amount of swing, or let's say the initial condition that I know I'm going to get right when I hit that linear region of operation. Okay? Again, this is exactly equivalent to what's inside of the parentheses there. I'm just rewriting it in a way that hopefully is slightly more clear in terms of where it came from. Okay? Does this kind of make sense to everybody? Or? So in other words, again, once I do this, or really the whole procedure is figure out how long you're slewing, then figure out from the edge of that slew condition to the final settling spec, how many tau does that take, add those two together, and you're done. Any questions on this? Or? Okay, great. So hopefully this is very clear. If not, by the way, you have a nice problem on this on your homework, so I'm sure it'll become 100% clear there. So with that, let's actually go ahead and move on to the next set of lecture notes. And what we're really going to be focusing on here is actually going to be quite useful for you guys in your homework, because what we're going to spend our time doing here is try and take all of the stuff we've been talking about over the last several weeks and try and put it together to say, okay, if I gave you some set of specifications for an amplifier, what's the methodology or the design procedure you would use to go about actually building that amplifier? Okay? Now, I should give you guys a reminder, which was that, as I said at the very beginning of the class, one of the most important things in analog design is not necessarily actually just taking a set of specs and building something out of them, but understanding where the specs came from in the first place so that you can actually modify the specs if that would make a lot more sense. But nonetheless, in order to do that, you also need to understand, if I did give you a set of specs, how would you build them so that you could then sort of give the appropriate feedback loop. Okay? So just as a sort of example, let's pretend that we're going to build a 50 megasample per second 11-bit ADC. Okay? And oftentimes if we're building these kinds of ADCs, there's going to be some kind of amplifier or amplifier-looking thing that we're going to have to put at the front that's going to essentially act as the first signal conditioning that we do for our ADC signal. Okay? So in particular, it turns out that even once I know sort of something as simple as the sample rate and the resolution of my ADC, I can already derive a whole bunch of specifications on my amplifier. Okay? So just as an example, let's first think about how accurate or what kind of total settling error I'm willing to tolerate for this kind of design. So if I've got an 11-bit ADC, what's the sort of relative size of my LSB relative to my full scale? How much smaller is one LSB compared to the entire range that I've got in my signal? Yeah, it's roughly speaking a factor of 2,000 smaller, right? So does that mean that I can just take, my entire error budget and assign it to this sort of accuracy, or is there going to be something else that might, be a problem? In other words, can I just say that my accuracy has to be something like, 1 over 2,000, or does it even actually have to be even smaller than that? What do you guys think? Yeah, it has to be even smaller, right? Because there's going to be actually lots of other error terms that I'm going to worry about. In particular, by the way, there's going to be things like thermal noise and capacitor mismatch and all kinds of these other unfortunate effects, right? So just because I really want to make sure that my amplifier does not cause any errors in and of itself, let's go ahead and assume that I'm going to make that accuracy spec 1e minus 4. Okay, so I'm going to really try and push that substantially down from what the sort of, 1 over 2000 would have been kind of the absolute minimum. If I then wanted to make sure it was really at the 11-bit level, I'd probably need another factor of 2 off of that. That would have been 1 over 4000. I'm going to say I want even another factor of 2 because I want to make sure I have some margin for all of the other errors. Okay? So I'm all the way down at about 1e minus 4. All right, so now given that this thing is a 50 megasample per second ADC, and I'm probably going to use sort of these switch capacitor amplifiers that we've talked about before, how much time do I have to actually settle to this error level? By the way, what's the period associated with 50 megasamples per second? It is 50 megahertz, yes, but I'm saying in time. How many seconds or picoseconds or nanoseconds? What is that in time? Okay, it's 20 nanoseconds, yes. Okay, so your full period for the entire sort of conversion cycle is 20 nanoseconds. Now, when we built those switch cap amplifiers, how many sort of phases did we have of operation per cycle? Yeah, there was 2 phases of operation, right? Okay, so roughly speaking, or rather, if we used at least a very simple sort of clocking scheme, how much settling time do we really have? Yeah, 10 nanoseconds. Okay, because for each phase, if we sort of budget it the same amount of relative settling time, which in general is kind of the best thing you can do, then indeed, you're going to have 10 nanoseconds of settling for your one stage there. Okay? All right, so what's next? What's the sort of dynamic range we need from this thing? And just as a reminder, dynamic range is kind of like the signal-to-noise ratio. Okay, you said 70 dB. So how did you get to 70 dB? That's actually correct, but how did you get there? Okay, yeah, so it's basically 6 dB per bit plus 1.76 dB of a sort of fixed offset. Okay, so that's not really exactly 70 dB, but again, there's going to be, I want to make sure I budget for some other error sources and, make sure that this is less than half an LSB and all that. So indeed, I'm going to make this 70 dB of dynamic range. Okay? All right, so now this is one where I'm just going to sort of arbitrarily decide what this is, but I'll explain why I did this in a second. So I'm going to decide that I want a closed loop gain of 8. Okay? The reason I chose 8 in this particular context is that the larger that closed loop gain for the first stage, the less the noise of everything else afterwards is going to matter. Okay? So again, this is somewhat of an arbitrary choice here, but just for the sake of the design example, let's take that one and play with it. Okay? All right, so finally, what should be my quote-unquote spec on power?
Low.
Well, okay, when you say low, let's be, slightly more precise so that you have the right idea. There's maybe just 3 letters you have to add after low to make it work. There we go, lowest. Okay, or minimum. Right? Because at the end of the day, I gave you a set of specs, and I want you to burn the minimum possible power or the lowest possible power you can to get those specs. Okay? So let's walk through and see. And by the way, I should mention, we're going to do one example design procedure here. I will not claim that this is the optimal design procedure, or that this is exactly what you should be doing when you do your homework as an example. But you'll see it's a reasonably good sort of starting point. Because as you'll see, we can really take sort of a fairly deterministic set of steps to actually get to exactly these specs that we're interested in. Okay? So, as I think I may have mentioned, even back when we did those very, very simple examples, it turns out that typically the very first thing you're going to do in your design procedure is actually something that's going to sound a little bit arbitrary, but we'll see tends to work reasonably well. So the very first thing we're actually going to do is pick our device bias points. Okay, or really, we could even say guess the device bias points. And by bias points, I really mean the V stars. Okay? So the other thing I'm also going to assume, just for the sake of simplicity now, is that let's assume that we've figured out that a folded cascode is essentially the right topology for us to be using from the standpoint of the input and output swing. Okay? So if I've got a folded cascode, let me just draw sort of one half of the structure or one side of the structure. It may indeed actually be a differential structure. But let me just draw one half of it so that it's sort of clear what are the real decisions we have to make in terms of the bias points. Okay? So let's say that that's my PMOS input device. Then I've got some NMOS current source, an NMOS cascode. And of course on the other side I've got another PMOS cascode and a PMOS current source. And that's my output. Okay? So let me just label these devices. Let me call this M-in, the input device. Let me call this the first current source. Let me call this the second current source. And let me just call both of these, this is a little bit of an abusive notation, but just bear with me. I'm going to call both the PMOS and the NMOS cascodes M cascode, or M cask. Okay? So now what I'm going to do, and since I have some experience with this, I'm actually going to make the guesses or the choices as to the bias point. But I'll explain why I did it in 1 second. Let me just assume, well, actually, let's just first list which choices you have to make, right? So you have to choose the V-in star, right? Which is the V star of the input device. Well, actually, no, you know what? I'll just give you a number, and then I'll ask you why I might have chosen that. So let's just say I chose that to be 120 millivolts. Okay, so this is the V star of the input device. Again, I'm going to pseudo-arbitrarily choose 120 millivolts. Now, what were the trade-offs I was making in my own head when I made that choice? What are the considerations in doing that? Okay, so because I used the folded cascode, you're right, that is going to set the linear input swing. Okay, I'll write that down. That is actually correct. That's usually not the first thing that I worry about, but you are actually correct. Okay? What else does this set? What is the sort of perhaps more important or more first order things that this is going to change? Yeah, it's going to affect our power, right? Because the lower the V star, the more GM you're going to get for a given bias current. What else is that going to affect? Yeah, exactly. So you said the input capacitance. That's another way of saying it's going to set the sort of FT of the device, right? Which indeed has a direct implication on the input cap. And we'll talk some more about that in a second. All right. Let's next choose as an example, I don't know, the V star of the current source. Okay? And let me actually do both of those. Is that right? Yeah, no, okay, I'll just do this one as being 200 millivolts. Okay? So, and also just for the sake of it, let me choose the second current source to be 220 millivolts. Okay? So what are the trade-offs I'm making when I choose those two? What's being traded against what? What did we say you want to do with current sources, or that you had to trade against each other with current sources? Okay, it's swing. Does the power really change with the V star of the current sources, at least to zero order? No, not really, right? Okay, so it's certainly swing. What am I trading on the other side? Noise, exactly, right? Because I want a low V star to get the most swing I can. But the lower the V star is, the more noise I'm going to pick up from that current source. Because remember, the lower the V star, the more GM per unit bias current, and therefore the more current noise per unit bias current. Okay? All right, and then finally I would probably have to choose the V star of my cascodes. And again, let me just make a somewhat arbitrary decision here of 120 millivolts. Now again, what's the sort of key things that I'm trading off when I make that choice, particularly in this folded cascode topology? What might make me want to have a low V star in particular? You said higher output impedance. It's kind of related to it, but let's in terms of, let's say, the parameters that I've already mentioned on the slide here. High gain. Yes and no. I mean, remember, the gain is largely, GMRO is not a direct function of V star, or it's not a very straightforward function of V star, but there's something that's a hopefully very obvious function of V star here. What was that? Slew rate. No, so this is the V star for the cascode. So the bias current, hopefully, and the the input swing is set mostly by the input devices. There we go. It's the swing, right? Because remember, those cascode devices, they're sitting right at that output node. Okay, so indeed, the lower I make that V star, the more swing I can get out of it. Okay? But what's the penalty or what's the trade-off I have to make? Why do I maybe not want that V star to be too low? What's bad about that? Okay, so you said the noise considerations. Remember, with a cascode device to zero order, right? Most of that noise current is going to be recirculating inside of the cascode itself, right? But there is one thing that turns out to be related to that, but for somewhat, it's not really that indirect, but it's somewhat of an indirect reason. Okay, it'll make the cascodes bigger. What's bad about that? There we go, right? So to say it another way, what you're trading is the FT of the device, right? Because the lower you make that V star, the lower the FT of that device will be, the more capacitance will be on that node. That will turn out to actually have a noise implication, but perhaps even more importantly, it'll have an implication on our non-dominant pole, right? And as we spent a lot of time talking about a second ago, there's really only specific places you might want to have that non-dominant pole, or in fact the pole zero doublet, that will basically work in our favor from the standpoint of settling. Okay? So the trade-off here is indeed that maybe I want it low to get a large swing, but I don't want it too low in order so that I don't mess up my settling response. Okay? Okay, so now this is where I can sort of maybe give you reminders to where a lot of this stuff was coming from. Because from a noise standpoint, as you guys hopefully remember, if we look at the noise current densities relative to the noise current coming from the input device, which again we usually define as that NF term, for this folded cascode, it's just going to be 1 plus VCS1 star over Vin star. No, I'm sorry, I flipped that. There we go. 1 plus Vin star over VCS1 star plus 2 times Vin star over VCS2 star. Right? Just remember, if you remember, the bias currents are such that you have to have twice the bias flowing in that MCS2 there as you do in the MCS1. Okay? So given those choices of V star that I made, you can quickly calculate this. It'll turn out that our sort of noise factor there will be, I believe, 2.1. Okay? And as you'll see in a second, that's going to be important because it's going to set a lot of the rest of the calculations that we're going to have to do. Okay? So this is basically my first step. I just basically choose my bias points. Again, somewhat arbitrarily in this case, but hopefully based upon some intuition about these trade-offs that I'm making here. And you can imagine you can always go back later and modify those bias points and see whether or not it can drive you towards a better overall solution. Okay? All right. So my next step is actually going to be to calculate the output swing. Okay? Oh, yes, question? Okay, so notice in the noise figure thing, or the noise factor thing, because I have double the bias current there, it's actually there's much more noise coming from that current source, so I upped the V star there to just help myself a little bit with that factor of 2. But, if you asked me exactly why did I choose 220 millivolts versus 200, because I happen to have the numbers for this already calculated. That's the real answer. But the principle is indeed that, of course, because the noise from here is more important, there is a stronger trade-off on that V star than there is on the current source of the upper device. It's a good question. Okay, so now let's go ahead and calculate our swing. All right? So what is the swing we can actually get at the output? What's that going to be set by? Okay, the V stars of that stack relative to, or rather, that's one piece of it. What's the other piece? Yeah, the supply voltage, right? So basically our V swing is going to be VDD minus the V star of the top current source minus the V star of the bottom current source, and then basically minus 2 of those cascode V stars. Okay? Now, there's one more thing I should mention, which is I'm going to do this particular example in a 0.18 micron technology with a supply voltage of 1.8 volts. Okay? Now, but unfortunately, in almost all realistic sort of products or scenarios you're going to deal with, even though the nominal supply voltage is 1.8 volts, there's almost always going to be this like plus minus 10% thing they add to you. Okay? Because it turns out it's hard to get exactly the supply voltage you wanted for lots of different reasons that I can tell you in more detail if you're interested. So at the end of the day, when we're doing our design methodology, we're probably not going to be able to use this 1.8 volts. We're going to have to say, look, I want to make sure this thing works with the absolute lowest supply voltage I ever get. Right? Which means that roughly speaking, I actually have to do this with 1.6 volts power supply. Okay? And this is, again, just to make sure that I still meet my signal to noise, dynamic range, accuracy, etc. specs with that 1.6 volt supply, which indeed is possible for me to have. Okay? Yes?
Well, would you actually want to do it over the range of like 1.6 to 2 volts?
You're right. I have to make sure that all of that is true over the range of 1.6 to 2 volts. But as you're going to see in a second, what's really going to be driving all of my calculations here is essentially the signal to noise ratio. Right? And I know that the worst case is going to be at the lowest supply voltage. Everywhere above that, unless something weird is happening, I should actually be getting better. So that's why I'm going to do this with 1.6 volts specifically. In other words, I'm basically saying, look, if I have to work in the worst case, I have no choice but to do the design methodology in the worst case. Okay? So if you run these numbers, and unless I made some silly mistake somewhere, I believe this turns out to be 940 millivolts. Okay? I should also mention, by the way, that everything I'm doing here is largely speaking for a single-ended example. I'll talk in the end about how things would change if you had a differential example. Okay? All right, so now that I've got my noise factor and my bias points and my swing, the next step is actually fairly straightforward, which is I'm just now going to calculate how big of an input swing I could actually have. Okay? And the reason I'm going to do that is very simple. Okay? What I'm going to do in 1 second is, once I know how big the input swing is, I can then actually calculate how big my capacitors need to be, based again on my signal to noise ratio or dynamic range constraints. Okay? So this step in some senses is actually kind of trivial because obviously now that I know what my output swing is, and I told you that I want a closed loop gain of let's say 8, then my maximum input swing is obviously just the output swing divided by that closed loop gain. Right? So in other words, this is just generally going to be VO swing divided by C, where C is the closed loop gain. And again, in this particular context, I chose that to be 8. Okay? Make sense to everybody? Or? Okay, so again, now that I've done that, here's where I'm actually going to basically calculate how big my CS needs to be. Okay? And I'm going to do that based, again, on the dynamic range constraint. Okay? And again, just sort of as a reminder, the reason I can do this is that to zero order, at least in that first phase of my switch cap operation, I'm essentially just going to be sampling my input onto that CS at the input. Right? And I know that when I let go of those switches, I'm going to have a KT over CS of noise sitting right there. Okay? So I can immediately already calculate how big that CS would, at the minimum, have to be to hit my 70 dB of dynamic range spec. Okay? So let's just go ahead and actually calculate that. So again, what we're basically saying is that the sort of SNR we want to have, which is kind of our RMS input voltage, relative to the RMS input noise, we want to make sure that that's equal to 70 dB. Okay? So if I really have this single-ended system, and I know that my VI swing is what I calculated up above a second ago, then basically the RMS value of that is just going to be something like the following. So it's going to be my output swing divided by C. That's like the peak to peak I can get at the output, right? Times a half, because that's going to set the amplitude of a sinusoid I could fit into that peak to peak, right? that whole thing squared times 1/2. And again, that 1/2 is just coming from the RMS calculation. Right? So you remember with sinusoids, the RMS power you get is 1/2 times the amplitude squared. So what's inside of the parentheses is the amplitude, and that 1/2 is just coming from the RMS. Okay? Is this clear to everybody? Or? I do indeed have two separate factors of 1/2. So this first factor of 1/2 here is just coming from, remember, the calculation I did here was what's the peak-to-peak swing I could do. Right? And so if I have to fit a sinusoid into that peak-to-peak swing, that's where that factor of 1/2 comes from. Okay, so then of course, the thermal noise, that's in this case actually easier. Oops. That thermal noise, of course, is just going to be kT over CS. Okay? So what I'm saying here is that, again, if I want 70 dB of dynamic range, that means this whole thing has to be a factor of 1E7. Okay? And, you can run some simple calculations. You'll see that this basically turns out to be a CS of 24 picofarads. Okay? Pretty nice hefty capacitor, but this is what it turns out I need in this particular case. All right? Okay, great question. So the question here was, is this the sort of input-referred SNR, or what exactly do I mean here? So I am being a little bit, let's say, fast and loose in the following sense. All I did here was calculate how much noise would I get contributed simply by sampling onto that CS relative to my input. Okay? So if your question was, well, hey, this isn't really all the noise I have in my system, aren't I also going to get some noise from the OTA itself? You're absolutely correct. Okay? So you could argue as to whether or not this 1E7 is really the right number. Right? What I might actually have to do is be a little bit more careful in that I should know really sort of how big this noise is going to be relative to the noise coming from the OTA itself, and then budget that accordingly. But procedurally, it's kind of the same thing. Right? Instead of this being 1E7, maybe it would be 2E7 or whatever that other factor would end up being. Does that make sense? Or, yeah, that's a very good question. So here you should not take the numbers really as, again, being set in stone. This is more just saying once you know how much noise you can have coming from that input stage, or really from that input sampling that you're performing, then you can use that to calculate how big the cap can actually be, or has to be, I should say. Is this clear to everybody? Or? Okay, great. So once actually, I can even do one more step, which is, given that I know that I want a closed loop gain of 8, what's my CF going to be? Or what does it have to be? Yeah, it's 3 picofarads, right? Because as we said, my closed loop gain is just 8. And so that means the ratio of CS and CF has to be 8. Okay? All right, so now that I've got all that, the next thing I can basically do is, and in this case I am going to actually make a guess. I need to guess what the actual feedback factor is. Okay? And so as a reminder, that actual feedback factor is of course going to be related to this closed loop gain, but it's not going to be identical, right? And in particular, if we looked at sort of this amplifier here, right, there's always going to be some input capacitance, okay? And so the reason I have to guess is because at this point, I don't yet know what that input cap actually is, right? I can make a sort of rough approximation, but really I don't exactly know what it is yet, okay? And as we had said before, what's really sort of going to change my guess or modify my guess is how I chose my V star in the first place, right? Because the lower I chose my V star, the larger the input cap will be, and therefore the smaller the feedback factor will be, okay? So to make this guess, let me just assume that that CI, the input cap, is equal to CF, okay? And again, this is really just a guess, but we're going to come back and see later if this is a valid guess or not, okay? In other words, I'm assuming my CI is 3 picofarads, all right? So if that's the case, that's going to say that my feedback factor is basically 1/10. Okay, and that's just coming from, I basically have 3 picofarads here, 3 picofarads there, 24 picofarads there. If you add those all together, you'll see you get 1/10. Okay? Make sense to everybody? Or? Now, by the way, I need to make this guess here because the very next thing I'm going to do is actually figure out how big the load cap at the output of the OTA has to be in order to have it satisfy a certain noise constraint, right? And if I don't know this F, I can't make that calculation, okay? So let's go ahead and do that next step. Okay, so the next step is really to calculate that load capacitance. And again, given the output dynamic range. Okay? Because really, just as a reminder, in that second phase, we're basically going to have the CS, the CF, the OTA, and again, it's going to be driving some load capacitance. And of course, that OTA has some input cap associated with it. Okay, so all I'm really going to do now is just calculate what that CL really needs to be, given the signal-to-noise ratio or dynamic range constraint in my system. Okay? So, much like we had done before, we just now have to do sort of our V signal squared, or RMS signal, relative to, in this case, this is going to be the output noise RMS. Okay? So as with before, this is going to be 1/2 times the amplitude of the sort of sinusoid I can fit in the output, which in this case is just going to be VO swing divided by 2, that whole thing squared. And then I just have to divide that by essentially, if you guys remember, it's going to be KT over CL effective. But times, of course, because I have those extra devices in my amplifier, and assuming that there's no internal filtering happening, which is usually a reasonable assumption to make, my integrated noise is also going to get multiplied by that noise factor. So I have to multiply this by the NF. And then finally, you have to also remember that we had said that at the output, you don't actually just get KT over C, but you get it basically multiplied by 1 over that feedback factor, right? Because remember, when we looked at this particular configuration, when we looked at essentially the impedance looking back there, it wasn't 1 over GM. It was essentially 1 over F times GM, which was multiplying up the noise. Okay? So this indeed is going to be sort of our overall expression for how big that load cap is going to have to be. And again, as we did before, which is not 100% correct, but is a reasonable thing for us to do for now, we're just going to say we again want that to be 70 dB. Okay? Again, in reality, you'd calculate exactly what the contribution of this is relative to the contribution of the input cap, and set those constraints appropriately. Okay? So this is now basically going to tell us that our effective load capacitance, if we run this calculation, has to be 7.9 picofarads. Okay, just trust me on that number. I ran it on my own calculator or whatever. That's the number. So to actually get to the real load capacitance, because as we'd said before, you have some additional loading from that feedback capacitance. Just as a reminder, you can say that the effective capacitance is equivalent to the load capacitance plus 1 minus F times the feedback capacitance. So at the end of the day, this is basically going to say that our load cap should be 5.3 picofarads. Okay, and again, I'd encourage you guys to just go back. You can double check my numbers here, but this is procedurally what I'm doing to actually calculate these numbers. Make sense to everybody so far? Or? Okay, great. So we're actually getting pretty close. Now that we have all those capacitance numbers, we can actually then figure out what our GM is actually going to have to be. Okay? Because remember, at the end of the day, the only reason you needed a certain GM was to drive load capacitors within a certain settling speed. Right? So, okay, so let's look at that settling speed. Again, just to find that GM. And in fact, I'll be more careful to find not just the GM, but also the DC gain we're going to need based on our accuracy spec. Okay? So let's first look at the required GM. All right? And just as a reminder, or rather, just maybe some additional information, for now I'm going to arbitrarily decide that I'm going to take that 1e minus 4 accuracy spec that I came up with, and I'm just going to split it equally between my two components. Okay, so if we go back here, then again we're basically saying that our dynamic error should just be that epsilon over 2, which is going to be 0.5 e minus 4. Okay? All right, so you guys tell me, assuming it's a simple single pole system, how many tau of settling do you need to hit that spec? And by the way, it might be easier for you to calculate it to 1e minus 4 first, and then just sort of, add or scale things appropriately. So what did we say was the rule of thumb? What was that?
2.3 tau.
Yeah, exactly. It's basically 2.3 tau per decade, right? So again, let's write that down. 2.3 tau per decade. So I've got at least 4 decades, right? That's just coming from the 1e minus 4. So that would put you already at about 9.2 or something like that. And it turns out the extra factor of 2 is something like 0.7 or 0.8 tau. So roughly speaking, at the end of the day, it's going to say that I need about 10 tau of settling here. Okay? And just as a reminder, we said that our overall settling time was 10 nanoseconds. So what does that mean our tau needs to be? Yeah, it's just 1 nanosecond, right? Okay, so if we go with that, then that's basically going to say that, as a reminder, our tau is just going to be CL effective divided by F times GM, right? And remember that F factor shows up for the exact same reason we said a second ago. The output impedance is not 1 over GM. It's 1 over F times GM, okay? So that's going to be our tau, and if we just take the numbers we had before, that's going to tell us that the GM we need is going to turn out to be 78 millisiemens. Okay? And by the way, I did not get anything wrong. There's no scale factors. This is indeed 78 millisiemens. All right? Okay, so by the way, once we've got that, we can actually also very quickly say what the drain current is going to be. All right? Because remember, after all, the drain current is just GM times the V star of the input device divided by 2, which in this case is going to be 4.7 milliamps. Okay? Make sense to everyone? Or? All right. So we got the dynamic settling. We can now actually do also the static settling as well, or the static error. And again, I'm just going to budget half of my error to be that. Okay, so remember here that we basically said this is again going to be 0.5 e minus 4, right? So this basically says that our loop gain has to be greater than 2 e4, right? But remember, we also said that our feedback factor was 1/10, right? So if I do my loop gain, that's just going to be F times AV0. That's again going to have to be greater than 2 e4, where F was 1/10, right? Which means that my closed loop, or excuse me, my gain just from the amplifier itself is going to have to be greater than 2 e5. Okay? In other words, I need an open loop gain of about 200,000 from this amplifier. Okay? So now maybe just I'll mention one sort of brief final thing before we close for today and pick back up with next time. Notice here that this gain spec doesn't really say anything about power consumption directly, right? Because in principle, I can always increase that gain by essentially increasing the channel length or something along those lines, right? It's only really the settling spec that directly says what your power consumption should be, right? Now, having said that, the practical issue you may indeed face is that with the voltage swings you want to get, it may indeed be very difficult to get this high of a DC open loop gain with a particular topology you used, right? So if you really need something that large, you might have to start involving gain boosting and other things like that, which then indeed would cost you some extra power. Nonetheless, however, to the first order, that gain boosting shouldn't really be driving explicitly your output cap, right? It's only driving transistors inside of it. So hopefully the power of that is not very large in compared to everything else that you're doing. But nonetheless, you can see that really the trade-off is that to zero order, you would like to just sort of put more error budget on the static things, because that doesn't necessarily cost you power. But if you do push it too far, it may just simply not be feasible to build that amplifier with that high of an open loop gain anymore. And that would tend you to push back towards having some basically larger error budget on the smaller settling budget on the dynamic side, but that directly costs you power, right? Because indeed, that dynamic settling, that's exactly what forces you to have a certain GM in your OTA, and that should exactly be what sets the power consumption of your design. Does this make sense to everybody, or? Okay, great. So as I said, make sure you show up for Pierluigi's discussion session tomorrow. He'll be going through a lot more sort of useful hints on the homework, and we'll pick back up and finish this on next Tuesday. So I'll see you guys all then.